Hi, I'm Paul Beckwith. I'm with the University of Ottawa, a laboratory for paleoclimatology. I'm going to give you an update on the Arctic, mostly on the Arctic sea ice, but I'll also discuss the vulnerability of Greenland when we lose Arctic sea ice and the implications to jet streams and global climate patterns, extreme weather events, atmospheric and ocean circulations around the globe. So the best place for Arctic sea ice graphs is just Google Arctic sea ice graphs, okay? And you get this site, also known as Nevin's site, and there's all kinds of stuff here, and I'll go through it a little bit. Now, this is ginger beer, by the way, non-alcoholic. Yeah, seriously, see, there's proof. Okay, so let me get the lights for improving contrast. Okay, so if you go Google Arctic sea ice graphs and just go here, there's all kinds of stuff and I'll show you some of it. So here we are, January 24th. This is the Arctic sea ice concentration. You can see where it's formed here. There's a whole bunch of different, this is Cryosphere Today. This is another organization, Ocean and Sea Ice, OSI, sea ice concentration. You can see these lines here. And this is the medium ice edge, 1981 to 2010. So you can see where we are right now. This is January 23rd. Okay, there's big chunks of ice missing where it would normally be in these sections. So we're even in middle of the winter, we're losing sea ice. This is the Arctic sea ice extent, October to now, and you can see this is the 1981 to 2010 average. This is the 2 sigma window, 2 sigma variation, so most of the years are within the gray area. This is the record low year, 2012 to 2013, and you can see what's happening. It's flattening out. So this is the area of the ocean with at least 15% sea ice. So you can have 85% open ocean, 15% sea ice, and it's included in this number. What you can see here is you can see what's happening. The red line here is what's happening in 2018. Okay, the red and red line operational product. And so this is sea ice extent again, much lower. This is from the European the European satellites. Okay, this is the U.S. satellites, National Snow and Ice Data Center. This is some more plot, so you can just go through. Now, if you want to elaborate and get more detail on any of these, just click on the graph, click on the plot. It takes you to the website, the source, and it gives you additional information. So here's the Japanese Arctic sea ice extent data. Again, it's showing, we're not very healthy. It's the winter. The ice is not forming properly. That means it will go quicker, won't be as thick. Lots of different graphs. This is very interesting here. This is global sea ice area. So if you take the area of the sea ice in the Arctic and add it to that in Antarctic, you can see what happened. This was in 2017. This 2017 here, 2017 is this line here. This was 2016 right here. Dropped off a cliff in 2016 here. This is an envelope of curves, of adding those curves, the Antarctic sea ice area and the Arctic sea ice area, and you can see that it's like the system is broken. It's like we're going into different regime, or a state shift has happened. We've crossed threshold. Okay, so there's huge disruptions, and that disrupts the heat balance on the planet, because ice is very reflective. When it's not there, open ocean is it absorbs the sunlight. Lots of other information, sea surface temperature here, and so on. I'm not going to talk about everything. I'll talk about some specific things. Look what's happening this year. This is the daily Arctic mean temperatures north of 80 degrees north. So if I click on here, we'll just have a look. So look at this curve here. You can go and you can click on previous years. This is 2017, so we did have spikes here, spikes here. This is the 1958 to 2002 mean is the green line. Okay, and This is 0 Celsius, is the blue line across here. So the Arctic is going to positive temperatures in the summer. This is the long-term average, and we're much higher, and we're getting spikes at the beginning of the year, so January, February, March, and also in the later months. Okay, so those the shoulder seasons here are, well, the winters are where we're getting extreme warming. In fact, if you go from, this is in Kelvin, but the difference is the same in like 10 Kelvin difference will be a 10 Celsius difference, or an 18 Fahrenheit difference. So the difference here, this is about 243, this is about 258, so that's about a 25 degrees Celsius different, multiplied by 1.8, so that's about 1620, that's about, what did I say, 25 degrees, so that's about 45 Fahrenheit difference. Okay, so we're getting huge warming here. 2016, 2015, 2014. So what you'll notice is, here in the winter, so January, February, March, first 3 months of the year, last 3 months of the year, are where we're getting the biggest effects of the most warming. Okay, let's go back to where we were. Okay, I can go here. I can just close this, I guess. It popped up. And there's temperature anomalies. There's all kinds of other information on the jet streams and things like that. Okay, this is a really good one to look at. This shows you the actual ice movement in centimeters per second, what it's doing. So all of this real-time data, this is the ice thickness. The ice thickness is a lot lower than it would normally be. It's not record low, but it's in that ballpark. All kinds of other stuff. This is Greenland melt extent. In 2017, you can see the spikes and things. You can click on it. In some years, one year it was very, very high, precipitable water, things like that. Okay, so all the information is there. It's updated. It's updated every day, and so it's generally, for the previous day. Lots of information there. Now, I clicked on, so if we go back to the top, all I'm doing is showing you some of the specific links. So I'm looking at the Arctic Sea Ice blog right now. So this is the most recent blog article. So this is the daily ice volume. So you can see in 2017 it was tracking at lowest on record, and then it was it wasn't the lowest on record, it moved up. There were a couple years that were lower here. There's different ways of displaying this data. This is a volume anomaly, so that's take what you have in the specific year, subtract the trend, the long-term average, and then you can get the trend, and you can see clearly the trend dropping. This is another view. This is 2017 is the red line here. You can extract the thickness, right? If you know what the volume is and you divide out the area, you can get the thickness of the ice, and you can see how the thickness has varied throughout the year. It hasn't got very thick. Okay, this is the average thickness, average Arctic sea ice thickness, and you can see that everything is getting lower. There's less and less ice there each year. This is some data showing the monthly volume gains in the ice through the years, in different, this is in December, okay, and then you can look at it in different years here. It's basically, here's the change, so this is the change in the central Arctic Ocean, less than 88 degrees north, sea ice volume in 1,000 cubic kilometers, and the gain here is extremely low compared to all of these other years. Here's another graph depicting that. This is the Japanese sea ice extent data. There's all kinds of data here, and what you can see is that there's just less and less of the ice. It doesn't matter which way you look at it. There's also information, where does the ice go? It doesn't just melt on the surface. It doesn't just melt underneath from the seawater. It also gets exported. This is export through the Fram Strait. So this is between Greenland and Svalbard. Okay, and what you can see in 2017 is the export completely stopped. From about in August and September, there was no export of ice. This is very unusual. Normally the weather patterns are such that you get a Beaufort gyre, the Transarctic drift, and you get export. But the patterns are changing. As we lose ice, the pressures are changing, the pressure differences are changing, the winds are changing. No export. We still had lots of sea ice loss from melting, but we didn't get any exported. There was a lot of warm water imported through from the Atlantic and the Pacific into the basin, mostly in the Atlantic, but there was no export. So there's different things happening which gives you year-to-year variability. Okay, now one of the most interesting comments here, sometimes the comments are even more interesting than the actual article, and this is the most significant comment. Okay, I'll just read it. This is a part of the thing I've been commenting about here for quite a while. My deep concern is that as the volume of ice declines in the Arctic, it starts a chain reaction. So we're talking about feedbacks, cascading feedbacks, the result of which is quite horrible, and that clearly we should all want to bend to avoid, bend every effort to avoid. As the ice melts, okay, the atmospheric heat engine first declines and then fails. As the engine declines in power, the system becomes unstable. Now, it talks about Francis. Jennifer Francis and many others show the jet streams weaken and destabilizes. As that happens, the rate of oscillation slows and dramatically deepens. So this is a slowing down of the variability in the Arctic. So you get because instead of getting very rapid spikes, you get very slow and lethargic stuff. Often a system will do that as it's about to fail or break. Hot air moves far north, cold air moves far south. So we're talking about the increasing waves in the jet stream as a very strong feedback mechanism for cold air leaving the Arctic and warm air going into the Arctic. Basically the Arctic warming like crazy, which is Arctic temperature amplification, which is 5 to 8 times the global average change in the high Arctic. Once the Arctic ice is gone, the only cold region up in the Arctic is Greenland. So it's a driving force for the circulation. So instead of global circulation centering on the cold Arctic, the cold North Pole, it is shifted over Greenland, and then that changes everything correspondingly. That changes the jet streams, it changes the Ferrel cell, Hadley cell, polar cell, it changes the ocean circulation, it changes everything, and it disrupts how we grow food and how we get fresh water, obviously. Huge societal implications. Okay, Greenland is much off center from the North Pole, so it pegs the circulation and stabilizes it to a degree, but in a different state from what we have now. We get a highly eccentric, or elliptical is what it means. It's not circular around the North Pole, it's centered over Greenland. So it's offset, it's displaced, the center of action. This doesn't help the oceanic systems, the currents. They fail first as the falling cold waters of the Arctic melt fail. Okay, with that, global ocean circulation fails. I wouldn't say it fails, but it reorganizes. You know, that sinking in the northern hemisphere, you know, Gulf Stream moves across, cools, is salty, or sinks to the seafloor, will happen at a lower latitude, probably it shifts. The oceans dramatically alter over short time periods. Once Greenland melts, nothing remains to drive the northern half of the global atmospheric heat engine. So the 3-cell atmospheric system, you know, Hadley, 0 to 30 degrees, Ferrel, 30 to 60 polar cells, they drive the weather for the entirety of primate, that's us, existence, fails. Rain no longer falls where it once did, the whole system changes. Throw everything out the window, models, everything's different. The Earth begins a rapid conversion to an odd semi-stable state with Greenland, and then to equable. Well, what that means is not much distinction with latitude. Human systems then fail, billions of humans die in short order. We want to avoid this at all costs. Okay, Antarctic, you know, can protect some remnants of the southern hemisphere, but this is a huge problem. So I'll have a part 2 of this video. Thanks for listening.